Okay, so thanks for the invitation to give a talk in the seminar. I'll be talking in the seminar about joint works with Maurice Ang and with Xin Sun, and also another joint work with Mattis Lehmkuehler. I will be, so the talk will be about a very powerful tool in random conformal geometry, which is known as conformal welding. And I want to present a few recent conformal welding results and also some of their applications. So I will start the talk by introducing three objects that we will be encountering later in the talk. So these are the Gaussian free field, Liouville quantum gravity, and the Schramm-Loewner evolution. And I will also very briefly explain what conformal welding is. So then in the second part of the talk, I will present our conformal welding results for LQG surfaces, and I will also be giving three recent applications. The first application is to the integrability of SLE. The second application is to random planar maps. And the third application is to the partition function of LQG surfaces with marked points. So I will start by introducing the Gaussian free field, Liouville quantum gravity, and SLE, which are three very important objects that we will be encountering later in the talk. So these three objects, they have several properties in common. So all three objects are random, and they can in some sense be viewed as planar or two-dimensional. The Gaussian free field is a random generalized function or distribution. Liouville quantum gravity can be viewed as a natural model for a 2D Riemannian manifold, while the Schramm-Loewner evolution is a random non-crossing curve in the plane. All three objects satisfy two natural properties that are known as conformal invariance and the domain marker property. The precise definition of these properties will not play a very important role. And a second property that all three objects have in common is that they describe the scaling limits of many discrete models. And we talk about universality because there is a large class of discrete models converging to these objects, such that the asymptotic behavior of the discrete model is typically not too independent of the details of the discrete model. So since these three objects have so many properties in common, it's maybe not so surprising that there are many interesting relationships and interplays between these objects. And this is what we will be exploiting in this talk. So I start by introducing the Gaussian free field. So the free boundary Gaussian free field in the unit disk, it is a Gaussian random field with mean zero and covariance given by the Neumann-Green's function, where we will use this definition for the Neumann-Green's function. So from this definition of the Gaussian free field, we see that the Gaussian free field cannot be well defined as a function. It cannot be well defined as a function because this Green's function is equal to infinity on the diagonal. So heuristically speaking, if we have some arbitrary point z in our domain, then h of z is a normal random variable with mean zero and infinite variance. But what can be argued is that the Gaussian free field is well defined as a random generalized function or a random distribution. So this means that if f is some smooth test function, then the integral of f against h is well defined. So this integral, it will be some random real number. It will have mean zero, and it will have covariance, which is given. It will have mean zero, and it will have a variance, which depends on this choice of a smooth test function f. Okay, so to define Liouville quantum gravity, we'll let gamma be a parameter between 0 and 2, and we'll let h be a Gaussian free field in some domain in the complex plane, for example, the unit square. So a Liouville quantum gravity surface, it can be heuristically defined as the surface for which the metric is given by the standard Euclidean metric times e to the power gamma h. So this means that it is a surface whose area measure has density e to the power gamma h relative to Lebesgue area measure. It is a surface whose boundary measure has density e to the power gamma h over 2 relative to the Euclidean length measure along the boundary of the domain. And the surface also has a metric or a distance function, which is defined such that the distances are locally rescaled by e to the power gamma h divided by d sub gamma, where d sub gamma is the dimension of the surface. The precise numerical value of d sub gamma is not known, but it's known to be some number which is strictly greater than 2. So this definition of an LQG surface doesn't make rigorous sense because h is a distribution and not a function, so it's not obvious what e to the power some constant times h means. But both the two measures mu and nu and the metric d can be defined rigorously by regularizing the field. So this is illustrated, this is shown in the last indented equation in the case of the area measure. So the idea is to let h sub epsilon be some regularized version of h, meaning it is a smooth approximation to h. So since h sub epsilon is a smooth function, we can use it to define an area measure. And it's possible to show that this area measure is converging as this regularization parameter epsilon is set to 0, and if we renormalize the measure appropriately. And a similar construction also works in the case of the boundary measure and in the case of the distance function or metric d. In this figure, you can see an illustration or simulation of the LQG area measure. So it's heuristically speaking the measure which has density e to the power gamma h relative to Lebesgue area measure. The red regions that you can see in the figure, they correspond to the high density regions where the Gaussian free field is particularly large. Whereas the blue regions correspond to the low density regions where the Gaussian free field is particularly small. So when we work with LQG surfaces in this talk, we want to view them as abstract surfaces that can be embedded into the complex plane in various different ways. So for example, in the figure, you can look at one LQG surface which has been embedded into the complex plane in 2 different ways. So we view this surface as the same as this surface, because if you look at the measures and the metric of this surface, then this is just the push forward of the measures and the metric of this surface under some conformal map phi. So it's possible to define many different variants of LQG surfaces by varying the precise choice of field h. So on this slide, I said that h is the Gaussian free field in the unit square, but it's also possible to choose h in a slightly different way. For example, we can let h be some Gaussian free field on some domain with some other topology. We can let h be a Gaussian free field plus some continuous function. We can let h be a field which is absolute continuous with respect to the Gaussian free field, and so on. And in all of these cases, the constructions which are mentioned on this slide, they still work. So in this talk, we are particularly interested in the variance of LQG that arise at the scaling limit of random planar maps. For example, in this figure, you can see a random planar map on the sphere. So I will not be giving any precise definitions related to planar maps in the talk, but roughly speaking, a planar map is just a graph which has been drawn on either the sphere or some subset of the complex plane. It has been proven that if this planar map has been sampled uniformly at random from all planar maps on the sphere, which has a given size, then it converges in scaling limit in some sense to the LQG surface, which is known as the LQG sphere. To be more precise, it is the square root of 8/3 LQG sphere, which means that this parameter gamma appearing in the definition is given by the square root of 8/3. Similarly, if we sample a planar map in the disk uniformly at random among all planar maps of a given size, then it converges in the scaling limit to the square root of 8/3 LQG disk. In this figure, we are considering again a planar map with disk topology, but now we also decorate the planar map by self-avoiding path. And we sample uniformly at random from the collection of planar maps decorated by such a self-avoiding path. So then again, we get the square root of 8/3 LQG disk in the scaling limit, but now the field describing the field h describing the disk will be slightly different. So this field will have logarithmic singularities at the points where the self-avoiding path start and end. and 1 over square root 6 describes the magnitude of this logarithmic singularity. So in the first 3 examples, we got LQG with gamma equal to the square root of 8/3. So the last figure is illustrating an example where we get LQG for a general value of gamma. So in the other examples, we were sampling a planar map uniformly at random from some collection of planar maps. But in the last figure, we are no longer sampling the planar map uniformly at random. So instead, we are sampling a planar map at random such that the probability of picking a particular map is proportional to the partition function of the loop OLN model on the planar map. And then it will converge to gamma LQG, where gamma is some function of the parameter n of this loop OLN model. Okay, so next I want to give a very brief introduction to SLE. So SLE, it is a conformal invariant fractal curve in the plane, which was introduced by Schramm in 1999. Schramm, he was introducing SLE as a candidate for the scaling limit of curves in statistical physics models. For example, it is conjectured to describe the scaling limit of the self-avoiding walk. And it has also been proven to describe the scaling limit of interfaces in the Ising model and also in several other statistical physics models. So Schramm, he realized that several of the discrete models that he was interested in, they were conjectured to have scaling limits having 2 properties in common. And these 2 properties are known as conformal invariance and the domain macro property. And he realized that there is a unique 1-parameter family of curves which are satisfying these 2 properties, and he called these curves SLE. SLE curves are associated with the parameter kappa, as when in the limit as kappa goes to 0, then the SLE curve becomes a deterministic curve. And then when we increase the value of kappa, then the curve is getting more and more windy or more and more fractal. Here in the figure, you can see a sketch of an SLE with kappa equals 2, and here an SLE with kappa equals 4. So there are many different variants that one can consider of SLE. So the variant of SLE I considered on the previous slide is what is called a chordal SLE, because it's defined in some simply connected strict subset of the complex plane, and it connects to points on the boundary of the domain. It's possible to argue that at least in some ways, the most natural generalization of this SLE, of this chordal SLE kappa, it is what is known as an SLE kappa with force points. So this is illustrated in the figure in the setting of 2 force points. So these 2 force points are shown in red in the figure. Each of these force points is associated with some parameter rho. For example, in the figure you see here, then this force point is associated with a value rho equals 0, while this force point is associated with a value rho which is negative. So if rho is equal to 0, then the force point doesn't have any influence on the behavior of the curve. If rho is negative, on the other hand, then the curve will be attracted towards the force point. So you can see that in this figure, the curve is attracted towards the right boundary of the domain. Similarly, if rho is positive, then the curve will be pushed away from the force point. In this figure, you can see that this value of rho is less than kappa over 2 minus 2, and then this attractive force is so strong that the curve will hit the domain boundary. So this SLE with force point, it was actually discovered only 3 years after SLE itself was discovered, and it has later been shown to arise in a huge number of different settings. So next we have the SLE loop. So this is a variant of SLE which is far less studied than this chordal SLE. It has been constructed for kappa between 0 and 8, and it was actually constructed for this full range only about 5 years ago. The SLE kappa loop is conjectured to be uniquely characterized by some axioms which are of a somewhat similar flavor as what you can see in this 3rd bullet point. But uniqueness is actually still an open problem. Finally, you have the conformal loop ensemble, or CLE. So this is a countable collection of random loops in the unit disk. So the CLE kappa was introduced about 15 years ago by Scott Sheffield, and it has later been studied in a large number of works. So finally, as part of the background, I want to explain what conformal welding is. So to do that, I let D1 and D2 be 2 copies of the unit disk, and I suppose that phi is a homeomorphism from the boundary of D1 to the boundary of D2. So conformal welding, it is a way of assigning conformal structure to the sphere that we obtain by identifying these 2 boundaries according to this homeomorphism phi. So if we identify the 2 copies of the unit disk according to phi, then it's clear that topologically speaking, we're getting a sphere. It's clear that if you look at this sphere away from this curve defining the interface of the original disks, then the sphere will have a unique conformal structure. But what is not clear is that we also have such a unique conformal structure across this curve, which is here denoted by eta. And an assignment of such conformal structure is known as conformal welding. Conformal welding is a classical and hard problem in analysis, and in general, both existence and uniqueness of conformal welding may fail. But if one has sufficient regularity of either phi or eta, then one can, in certain cases, guarantee the existence of a unique solution. So in this talk, we are interested in conformal welding in the setting of LQG surfaces. And I will start by giving some discrete motivation in the setting of planar maps. So this figure is illustrating that we have a projection between the objects on the left and right sides of the equality sign. So on the left side of the equality sign, we have a planar map with disk topology, which has been decorated by this self-awarding path. In the right part of the figure, then we have this pair of planar maps, and we require that the length of this blue curve on the map M1 is equal to the length of this blue curve on the map M2. And the projection simply works by taking these 2 planar maps and then identify them along these blue curves. So this projection is illustrating one key strength of conformal welding. So the planar map that we're looking at the left part of the figure is a rather complicated object because of the presence of this self-avoiding path. These 2 objects in the right part of the figure are in some sense much simpler objects. But because of this projection, if you want to study the object in the left, on the left side of the figure, then we can equivalently study the objects in the right side of the figure. So this is illustrating one key strength of conformal welding because it often allows us to divide very complicated surfaces into simpler pieces and then study the complicated surface by studying these simpler pieces. And we will see several examples of this a little bit later in the talk. In a joint work with Ang and Sun, we proved the continuum counterpart of the projection on the previous slide. So we are considering 2 Liouville quantum gravity disks shown here in green and blue. And then we are conformally welding these 2 disks together along these purple curves. When we're doing the welding, we're doing it such that if we consider some small segment of length epsilon on this purple curve, then it is identified with some small segment of length epsilon on this purple curve. So we prove that this conformal welding is well defined. We prove that if we do the conformal welding, then the resulting object is still what we call an LQG disk. And we prove that the interface between the original disks is given by an SLE kappa rho curve. So you can see that all the disks involved in this result, they have 2 mark points, which are shown here in red. So at each of these marked points, then the field defining the disk has a logarithmic singularity, and the magnitude of the logarithmic singularity is this number, which is shown next to the point. For example, nearby this point, then the field looks locally like a Gaussian free field plus beta times a logarithm. The rho values of the SLE kappa rho that you see here, it is given by some explicit formula of gamma and of beta plus minus. The special case when gamma is equal to beta plus minus equal to the square root of 8/3 is describing the scaling limit of the planar map with self-loading path on the previous slide. So this is a rigorous statement which can be obtained by combining the result stated here or presented here with the work of Gwynn and Miller. So all of this, so finally I want to mention that all of this result is proved in the work with Ang and Son. Then the proof is relying heavily on earlier related works due to Sheffield and by Duplanty, Mueller, and Sheffield. Okay, so next I want to present an application of the conformal welding result, which was presented on the previous slide. So by applying the conformal welding result on the previous slide, we are able to prove an integrability result for the SLE kappa row curve. So in these two figures, you can see SLE kappa row curves with different choices of row. So these SLE kappa row curves, they will divide the unit disk into several connected components, and with probability 1, there will be a unique component which has the point 1 on its boundary. So this unique component is shown in light blue in the figure. Okay, so then we consider a conformal map psi from this light blue component and to the unit disk, which is fixing on location of 1 and which also sends these green points to the points plus minus I. And then we can derive some exact formula for the moments of the derivative of psi evaluated at the point 1. So you can see that the formula we are proving, it contains a function f, it contains a function alpha, and it also contains some constant lambda 0. So all these functions and this constant are defined under the theorem statement. So we first set q equal to 2 over root kappa plus root kappa over 2. Then we define the double gamma function by this integral. So to be more precise, we are using this definition when the real product of z is strictly positive, and otherwise we are defining a function by analytic continuation. Then we define the function f as a ratio of these double gamma functions. Then we are defining the function alpha in the fourth line implicitly via this quadratic equation. And then finally, we're defining this parameter lambda 0 by this formula. If lambda is greater than lambda 0, then this, or greater than or equal to lambda 0, then this moment that we're considering here is infinite. So as mentioned before, the proof is based on couplings between SLE and LQG. And in addition, we're using exact formulas from Liouville conformal field theory, and also exact formulas for planar Brownian motion. So in most literature, where one proves exact formulas for SLE, then the proof is based on Ito calculus methods, and it's using a definition of SLE via Loewner chains. So this more classical method, it doesn't seem easy to apply in order to prove this moment formula. And it's interesting to see that we can get this result, which is purely about SLE, by using this coupling between SLE and LQG. So as mentioned before, the starting point of our proof is the conformal welding result that I presented earlier. We are actually proving, so we're actually applying a slightly more general variant of this conformal welding result. So we're considering the case when this blue disk has an extra alpha log singularity at the point 1. So this conformal welding is still well defined, and the resulting disk is exactly the same disk as before, except that we have this additional logarithmic singularity again at the point 1. So the curve eta in the setting of this extra marked point, it will now be a curve which has a Radon-Nikodym derivative relative to SLE kappa rho, which is given by this particular power of the derivative of the conformal map psi. So the conformal map sending the blue domain to this disk, evaluated at the point 1. So once we have proved this conformal welding result, it's not so hard to obtain this conformal welding result via an application of Girsanov's theorem. So this slide is illustrating the main idea of the proof. So the main idea of the proof is that we are considering the length, considering this boundary arc L shown in red, and then we're computing the law of the length of L in 2 different ways. We're computing the law of the length of L in one way by using the left side of the welding identity, and we are computing the law of the length of L in another way using the right-hand side of the welding identity. So when we compute the law of the length of L using the left side of the welding identity, then our formula will involve this moment of the derivative of psi evaluated at 1. The formula will involve this moment because of this form that the Radon-Nikodym derivative is taking. So we have these two formulas for the law of the length of L. We can set these two formulas equal to each other, and we can solve for this moment. Okay, so when we are computing the law of the length of L, then there are mainly two inputs that we will be using, and these two inputs I want to present on the next few slides. So the first input that we're using is the result due to Remy and Zhu. Remy and Zhu, they are considering the LQG disk with 3 mark points. They're considering one boundary arc, which is here called L, and they're giving an explicit formula for the law of the length of L. It's not so hard to argue that the law of the length of L is given by some power law with some explicit power. But what is very hard is to identify the constant appearing in front of this power law. And Remy and Zhu, they compute an explicit formula for this constant by using techniques from Liouville conformal field theory. Okay, so when computing these boundary lengths, then the second input that we will need is the result stated on this slide. So here we are considering a disk with 2 singularities on the boundary, and then we are computing an explicit formula for the joint law of the left and right boundary arc lengths. So the disks are considered on this slide. They are in some sense easier objects than the disk which is considered on this slide, because the number of mark points is just 2 instead of 3. But the problem we're considering on this slide is harder, because we don't just want the marginal law of one boundary arc length, but we want the joint law of both boundary arc lengths. And we're actually only able to write down explicit and relatively short and nice formulas for this joint law in the special cases when the singularity is taking this value or this special value gamma. So the proof of these two formulas that you can see on this slide is based on a completely different technique than the formula that you saw on the previous slide. So the proof on this slide is using a particular encoding of a Liouville quantum gravity disk in terms of a planar Brownian motion. So the exact formulas that you see here, they are obtained from exact formulas for a planar Brownian motion. Okay. So that's all I wanted to say about the integrability of this SLE conformal derivative. And next, I want to present another conformal welding result and also an application to random planar maps and the SLE loop. So in a work with Ang and Sun, we proved that if we take 2 Liouville quantum gravity disks, then the conformal welding of these 2 disks is well defined. And we prove that the resulting object we get is a Liouville quantum gravity sphere. And this LQG sphere is decorated by an SLE loop, which has parameter gamma squared, where gamma is the parameter of the LQG. And it is such that this SLE loop it is independent of the sphere. So by combining this conformal welding result with a result due to Gwynn and Miller, then we get a scaling limit result for planar maps. So we consider a planar map with spherical topology. Then we decorate it by a self-voiding loop. And then we can show that this object converges in the scaling limit to this LQG sphere decorated by this independent SLE loop in the special case when gamma squared is equal to 8/3. Okay, so finally, I want to present this application to the partition function of LQG surfaces with marked points. So I'll start, as we start by considering a planar map with the loop of n model. So this, what this means is that we consider a random planar map, big M, which has been sampled at random, such that the probability that our planar map is equal to some fixed map, little m, it is proportional to the partition function of the loop of n model on the planar map, little m. So what I mentioned very briefly earlier is that this planar map in the scaling limit, it is conjectured to converge to a Liouville quantum gravity disk. What is also believed to hold is that if we look at the scaling limits of these loops, then this is given by this collection of random SLE type curves known as a conformal loop ensemble, or SLE. So this was the variant of SLE that I was briefly introducing on this slide. Okay. So what is also believed to hold is that the parameter kappa of the SLE is given by this formula, where n is the parameter appearing in the loop of n model. And it is also believed to hold that the LQG parameter is given by the square root of kappa. So the conjecture, which I've stated on this slide, it's actually only believed to hold in what we call the dilute case. So the loop of n model, it has parameter n, but it also has two additional parameters, which are also called g and h. And the conjecture is only believed to hold if g and h take one very particular value. So there's actually also another case, which is also quite interesting. So there's also another case, which is called the dense case, and g and h can also take values in what is called the dense regime. Many of the results I will be presenting later in the talk, they actually also hold in this dense case. But just to be concrete, I choose to focus on this dilute case. So next we consider a generalized variant of the model considered on the previous slide. So here we are considering, we let m be some natural number, and then we're considering a planar map with loops which have m additional marked vertices. So we have one vertex x1 and one additional vertex x2. So for each subset of points B, then we let n sub B be the number of loops surrounding the point in B. For example, we have n sub 1 equals 1, since there's one loop around the point 1. We have n2 equals 2, since there are two loops around x2, and we have n sub n2 equal to 0, because there are no loops around both points. For any such subset of points, we also associate a real parameter sigma, and we also have some parameter lambda, which is greater than or equal to 0. So now we are sampling our planar map at random, such that for any fixed planar map, little m, then we again let the planar map, the probability of picking the particular map, little m, it be proportional to the O of n, to the loop of n model partition function of m. But now we also are multiplying by this term depending on these nesting statistics defined via nb. There should actually also be an expectation around this term, which average over all possible loop configurations. We also multiply by this term at the end, which is giving us some exponential penalization of surfaces with large area. The area of the planar map is just the total number of vertices of the planar map, and when we sample this planar map at random, then we are assuming that the boundary length of the map is fixed, whereas the number of vertices in total is random. So remember that when we're considering this random planar map without any marked points, then we were believed to get an LQG disk with a CLE in the scaling limit. And some variant of this result is also believed to hold in the setting with additional marked points. So it's believed that we still get some LQG disk in the scaling limit, and this LQG disk will again be decorated by some SLE type loops. But now the disk will also have some marked points, which correspond to the scaling limit of the marked points on the previous slide. So on the previous slide, we had m equals 2 marked points, and here we have m equals 4 marked points. So before I describe more precisely the object that we expect to get, then I want to give some heuristics in the setting of planar maps. So suppose that we are sampling a planar map as described on the slide. So if we are if we first sample the planar map with marked points, and then afterwards we add loops, then if we do such a reweighting according to nesting statistics, then this will change the law of the loop configuration. So just to be concrete, suppose that we have lambda equals 0 and that all sigma b's are positive. So then we will favor loop configurations which have a large number of loops around the marked points. But if we sample a planar map as described on this slide, then we will actually, and the collection of loops as described on this slide, then we will actually not only change the law of the collection of loops, but we will actually also change the law of the planar map. So in the example I just mentioned, then where we're favoring configurations with lots of loops, then we will favor planar maps which have a huge density of vertices around these marked points. So we're favoring maps with a huge number of density, with a very large density of vertices around these points, because if we have many vertices around these points, then there will typically be a lot of room for adding a number of loops. So this heuristic is explaining that in the scaling limit, we expect to get a limiting object where both the LQG surface and the CLE has a law which has been changed. So we are arguing in our work that if we consider the field age obtained in this scaling limit result, and then we are doing the reweighting according to these nesting statistics, then what should happen is that the law of the field has been is reweighted by this term that you can see in blue. So here this parameter alpha sub j is related to the parameter sigma sub j via the formula that you can see here. I will be coming back to this formula a little bit later in the talk. And it's not so hard to argue via Gershanov's theorem that doing this reweighting, if it corresponds to adding logarithmic singularities to the field. So the field, which is pairs in the scaling limit result, it will have logarithmic singularities at each of these 4 marked points. The resulting field actually happens to be exactly the field which is arising in the setting of Liouville CFT, and which was defined rigorously in the work of Huang, Rhodes, and Vargas. We also argue in our work that if you look at the scaling limit of the loops on the planar map, then this should be given by a variant of CLE, such that, heuristically speaking, the Radon nuclear derivative of our CLE relative to the regular CLE is given by this term that you can see in blue. So this term that you can see in blue, it actually doesn't make rigorous sense in the continuum, because if B consists of a single point, then n sub B will actually be infinite with probability 1, because there are infinitely many loops around each point. But I will show you a little bit later that one can make rigorous sense of this term. And I can also remark that in this figure is only showing the outermost CLE loop, but actually there are also inside each of the CLE loops you see here, there are also a number of smaller CLE loops. Okay, so on this slide you can see the object that we were studying on, or that I was introducing on the previous slide. So for this object, there is one very interesting result that one can prove. So this LQG disk, so if you look at the CLE on top of this LQG disk, then this CLE is dividing the LQG disk into a number of smaller LQG surfaces. For example, we have one LQG surface here, we have one LQG surface here, a third LQG surface here, and so on. So what is possible to prove is that these smaller LQG surfaces, they are actually entirely independent of each other. And if we condition on the length of their boundary lengths, and in addition, the law of these smaller LQG surfaces is actually identical to the law of the original surface. If again we take into account that the boundary length is different, and we also condition on which mark points that fall into the various surfaces. So for example, this LQG surface is the big LQG surface is an LQG surface that we call the LQG disk with 4 marked points. Whereas, for example, the LQG surface inside this loop, it will be an LQG disk with 2 marked points. So the result stated on this slide, it's not at all surprising from the point of view of planar maps, because actually the exactly analogous property holds in the setting of planar maps. But in the continuum, the result is very non-trivial, and the proof is also carried out purely in the continuum using very different techniques from the discrete setting. So next, I introduce the partition function of the surface. So if you look at the LQG disk on this slide, then it can be associated with 4 parameters. The first parameter is sigma, which is describing this reweighting according to the nesting statistics. We have a parameter kappa, which is the parameter kappa of the CLE. We have a parameter lambda, which is represents this penalization that we do of surfaces with large area. And we also have a parameter L, which is just some positive real number giving the boundary length of the disk. And we define the partition function of this disk to be equal to the partition function of the disk with no marked points, which is explicitly known from other literature. And then we are multiplying by this integral. So when we were defining our disk, remember that we took the disk without marked points and we reweighted by this terms in blue. Therefore, and this is if we condition on the location of the mark points. So therefore, in order to get the partition function, it's natural to multiply together these 2 terms, take the expectation, and then integrate over all possible locations. Integrate over all possible locations of the marked points z. These 2 terms that you can see in blue, they are independent of each other, so we can factorize this expectation is factorizing. Making sense of the expectation of the first blue term is quite easy because the field is Gaussian. Making sense of the expectation of the second term in blue is much harder, and this is something we are doing in our work, and we are defining the resulting. The expectation we're defining a function phi denoting this expectation. When proving that this function phi is well defined, then in particular we need to derive some strong spatial independence results for CLE, and we also have to use an explicit formula for the law of the CLE conformal radius, which was first derived in work of Schramm, Sheffield, and Wilson. And this exact formula for the CLE conformal radius is actually also the reason behind this explicit relationship between the parameters alpha and sigma. So this partition function z, it's part of interest because it is we conjecture that it describes the scaling limit of the discrete partition function in the setting of planar maps. Another reason it is interesting is because it is closely related to Liouville CFT. In this in this last indented equation on the slide, you can see an explicit formula which relates 3 very interesting objects. The first object is this partition function z. The second object is this function phi, and the third object is this constant big C. So this constant big C is appearing in Liouville CFT, and it's very closely related to what is called the Liouville CFT correlation function. So to be more precise, if we take this constant C and we integrate it over the boundary length L of the disk, then we get precisely what is called a Liouville CFT correlation function. So this formula is giving an explicit relationship between these three interesting objects. So this function phi is partly of interest just because it is quite interesting, observable for SLE. It's also of interest because it is related to what is called we call imaginary LCFT. So in LCFT or Liouville CFT, then this parameter gamma of the theory is typically chosen to be real and typically between 0 and 2. But many of the objects actually also make sense when gamma is imaginary or complex. And the case of imaginary gamma is particularly interesting because it is related to the problem of study of defining a CFT for SLE. Okay. So then going back to these partition functions. So in our work, we are deriving a recursive formula for the partition functions z. So when the number of marked points m is equal to either 0 or 1, then one can compute an explicit formula for z. When the number of marked points is greater than or equal to 2, then we derive a recursive formula for z. And in this proof, we're using the results stated on this slide. So on this slide, you see that if we have a disk with 4 marked points, then by using an SLE, we can break this disk into a number of smaller disks, which have strictly fewer than 4 marked points. And by using this result, it's possible to argue that the 4-point partition function can be expressed explicitly in terms of the lower order partition functions. So when we prove this latter statement, then we're also using a continuum counterpart of what is known as the peeling process of planar maps. So this continuum counterpart of the peeling process, it is relevant because it allows us to derive the joint law of the loop lengths in the figure I just showed. So you see that in this figure you have a number of SLE loops. Each of these will have a random length. And we are able to obtain an explicit joint law of these lengths by using this continuum peeling process. So we get this rather complicated recursive formula for the partition functions z. In our work, we're not attempting to simplify this recursive formula, but we do use the recursive formula to study the admissibility question. So we say that some parameters are admissible if the partition function is finite. And we prove a number of so we don't fully characterize the set of admissible parameters, but we prove several of its properties. So we show that when m is equal to 1, so the number of marked points is equal to 1, then we always have admissibility. If m is greater than or equal to 2 and this lambda is equal to 0, then we never have admissibility. So partition function is always infinite. So on the contrary, if lambda is positive and sigma sub b is strictly less than sigma sub I for all subset of points b with strictly more than 1 point, then we always have admissibility. But on the other hand, if we choose some arbitrary subset of points with more than 1 point, and then we choose the associated parameter sigma sub b arbitrarily large, sufficiently large as compared to the other parameters, then the partition function will always be infinite. Okay, thanks.